Thank you, guys. Thank you. Let's do with the lights. Everyone got a handout? It's all good? We'll do the lights. We'll just get this moving along. Okay, so yeah, another introduction to astronomy. I thought we'd start with a video. We've got a few videos tonight. We're going to start with one. So that's inside Jezero Crater, February 2021, landed there. And that's what we're looking at landing. That's the Perseverance, NASA's Perseverance rover. So that's it managed to take a selfie of itself. Pretty cool. Yeah. So tonight's talk is NASA's Perseverance rover, searching for ancient life on Mars. And this is the way I've organised it. So this is what you're going to learn about tonight. We'll talk about some background, what we knew about Mars before they sent Perseverance. So what was the playing field when it went there? We'll then talk about Perseverance's main goal, its objective, and its 7 science instruments. We'll talk about Jezero Crater, and I've got lots of visuals for that too. I really want you to go away tonight, when you close your eyes at tonight, when you go to bed, I want you to be able to imagine you're there, you know exactly what it's like. So I hope we're going to achieve that today. Then we'll talk about the important discoveries that Perseverance has made to date, but far more importantly, the implications. It's one thing knowing about what something's being discovered, but it's more important to know what that tells us, the implications of that. And then we'll have a summary and conclusion, and then we'll take some questions. So let's look up first, background, what we knew about Mars. The bottom line is, and we're going to show you some of the lines of evidence for that, is that we know from previous orbiters and landers and rovers that Mars now, as you know, is dry and cold, but it was once warm and wet. Water flowed freely on its surface and subsurface as well. So let's have a look how we found that out. This was an image taken from Mariner 9, the very first orbiter to go around any planet for that matter, 1971. Very grainy image, but you can see there all the networks of canals that are going on. It doesn't take too much imagination to realise, whoa, something liquid has flown through those. which of course what's the most abundant liquid in the universe? Water. This was a topographic image taken from an orbiter around Mars, and whereby your red and purple around here is high elevation, and then going through to yellow, green, and then to blue for low elevation. And you can see here these huge big canyon, sort of a system of canyons there. That's 3,500 kilometres long, twice the length of New Zealand, of these big outflow channels. You can see where water's just gushed from the highlands down here. And a lot of evidence to suggest this whole area here was actually a great ocean, the Northern Ocean in Mars, which I've got a picture of shortly. They could see plenty of these. This is Gussive craters, so very large craters. This is actually about 3 times the size of Lake Taupo. That's 166 kilometres across that crater. There was Gussive crater where the Spirit rover landed in January 2004. But they saw lots of huge craters like this. But importantly, the craters had a nice lake bed on them with sedimentary rock, usually mudstone and clay, most of it there, but right along very flat surfaces where clearly water had been, with channels going through them here, some of them clearly going in or going out as well. So saw a lot of those there as well, and then I said the Spirit landed there. Curiosity rover, 2015, landed in Gale crater. Roamed around here. This is a lovely image. I love this image of Dingo Gap in Gale crater. But you can see the crater all here, and you can see very clear evidence of erosion that's been going. Look, all the smooth stones and so on. And this is a nice flat lake bed here. But the findings from Curiosity concluded that Mars was habitable, in other words, it could support life 3.6 billion years ago. So that's where we're starting off from. This is an artist's impression of what Mars may have looked like about that era. You can see the great Northern Ocean there, and just huge amounts of water. So it could certainly sustain life 3.6 billion years ago. So that's where we leave off. Let's now look at Perseverance itself and look at some of its instruments. Its objective was not so much to search for habitability anymore, but to move on and look for any signs, what are called biosignatures, proteins, telltale signs of previous life, fossiled life. Look for signs of ancient microbial life. This here is the rover. This is actually a mock-up, a model of the rover, but it's a 1-to-1 scale, just to give you an idea of the size, about the size of a small SUV. The mast up here, which we'll be looking at, the tower there is about 2 meters high, and this here is about the size of a small SUV. So you can see the size of it, put it in perspective there against the technicians. This is a diagram of it here and of the science instruments, which we'll now have a look at. So first of all, at the top of the tower there, you have 2 camera systems. First one is a Mast Cam Z, which is sitting here. And that's a series of cameras and videos. It takes high definition color images from quite a distance. It's got a very capable zoom system, so the rover, if it spots some rocks in the distance, high definition cameras can zoom in there and also sweep across the landscape. So back at NASA, they can get a good idea of what it's looking at, and if they see of anything interest, they can zoom into it. SuperCam, which sits right beside it there, also uses a series of cameras, but also it's got on an infrared and a green laser that can, if it sees rocks up to about 7 meters away, it can then beam, a laser beam, either in visible light, green, or in infrared wavelengths, to excite atoms and molecules on those rocks, get them excited, analyze the light that comes off them. It usually vaporizes small parts, analyzes that light through spectroscopy and gets a good idea, just a very rough idea of elements and some of the molecules that are sitting on those rocks. And it's able to do that from a bit of a distance, so it's able to map out where things are, where certain minerals and elements are. So what I'm going to do, I'm going to take you through these instruments, and then we're going to go through the actual process and the order in which these instruments are used when it does see something of interest. Then on the end, there's a 2 meter robotic arm out here. in itself, that's pretty sophisticated, with a instrument turret on the end. And on the turret, don't you like their acronyms? Sherlock and Watson. Yeah, so Sherlock is a spectrograph with UV light, whereby it directs ultraviolet light, excites atoms and particulate molecules and stuff, and then looks at the spectroscopy of it, and looks at the light that gets scattered off that. That gives them a good idea of the chemical composition, particular organic molecules and minerals formed in water. The handouts go into a lot more detail about this, but I'm going to show you shortly how this is key to perseverance. You might say, well, Curiosity does some of that, doesn't it? It does, but this is more fine-tuned. Curiosity used to just blitz and just totally vaporize chemicals to see what was going on in there. Perseverance uses a special technique called Raman spectroscopy, where it just excites it, and then looks at the light that gets scattered off various molecules to get an idea of the chemical bonding that's going on. So it preserves what it's actually zapping, as opposed to totally vaporizing something. So that's got ultraviolet light. So you had green laser and infrared for your supercam. Then you sort of then they'll move up to an area of concern, use the 2-meter robot, and you've got Sherlock, which is ultraviolet light to excite molecules. Then you've got Pixel, and that focuses X-ray beams at rocks of interest, and that's able to, once again, analyze the spectroscopic light that comes off and give an idea of what elements are in there, like iron, nickel, and calcium, and so on, microscopic levels. Then you've got RIMFAX at the end. This is a radar system that sends radar beams down underneath the ground and can get an idea of the subsurface, the structure and geology of the subsurface, up to 10 meters. 10 meters, probably the width, the length rather, of this room, 10 meters. So it just fires radio waves and measures and then analyzes the waves as they bounce back, and it can tell the subsurface up to 10 meters deep. Rocks, if there's ice there, where the various layers are going, and so on. MEDA is a weather station in the middle. It's got various sensors right all over the rover that looks at wind speed, temperatures, dust conditions, and so on. Then there's MOXIE, and that sort of sits more in the belly, just to the side and into the belly of the rover there. And that's an experiment which proved to be very successful. You probably know that the Martian atmosphere is mainly carbon dioxide. And if we're going to go there, we're going to want oxygen to breathe. You're going to want oxygen for your to make water further, to get water from. You're going to want oxygen to for various other functions. Rocket fuel in particular, it's very important for. So their experiment was to subtract atmospheric carbon dioxide and convert it into oxygen. And really, it's sort of demonstrating technology for future missions. So as I mentioned, breathable air and rocket fuel are the two biggest spin-offs from there. Then the other thing is, at the end of the turret, is it's got a fancy drill. It's not just a normal drill. It's a nice close-up of it there. And that's actually able to, first of all, it's got 3 functions with it. It's got the drill's able to go into rocks. It's able to go into regolith, that's just into soil, but it's got an abrading tool that's almost like a brush and to scrape away. So if it sees a rock with some soil and dirt and stuff on it, it wants to clean it all up so it gets a nice sample. So it's able to clean the rock up beforehand and then drill down into the rock. And once again, with the rock, it's instead of just drilling out and just getting a whole big mix of dust and content from the rock, like Curiosity would have probably done, throw it in the oven, and Curiosity pretty much baked its samples and see what came out of it. Perseverance preserves the rock, takes a nice core sample out, preserves it, puts it in a titanium tube, and hanging on to it for hopefully in the future a mission to go and retrieve those samples, bring them back to Earth, and actually under high-end laboratories on Earth, and get a much better definitive idea of what those rocks are and date them and so on. So it's a pretty sophisticated drill. So just how it all works in 4 basic steps. So it's driving along, they are scanning the landscape, suddenly something will be of interest because it's panning around, something will be of interest, the astronomers say, look, that looks interesting. The supercam can fire its laser, it's got infrared and green laser, to have a look at the rock, look at the spectroscopy of it, and infer the elemental composition, the elements that are there, to map them out. If they're still interested in it, then they can drive up to it close, You've got the arm that's 2 meters long, so it can get the abrasion tool out, clean all the dust out to expose express rock. The Watson camera, which I'll show you how close it gets. The Watson camera uses detailed close-up images, and I've got a video of that shortly, just illustrating the high definition the Watson camera's got. Step 3, Pixel first of all fires the X-rays at it, gets an idea of the abundances of various elements. Sherlock then fires the ultraviolet light at it and identifies specific minerals or organic molecules and potential biosignatures. And then step 4, if I think, yes, this is really interesting stuff, we're definitely interested in getting a sample of this to possibly send back to Earth. The drill is able to take a core sample off it, put it into its titanium tube, and then store it for future analysis on Earth. There was big plans for that. They've all been put on hold in the meantime. Yeah, okay. So now the other thing at the back of it, people say, how is it powered? Nuclear power. It's got what they call an RTG, or radioisotope thermoelectric generator, with plutonium-238 at the back. Then naturally decays, generates heat, and that in turn is able to generate 110 watts of electricity, giving the rover about a 14-year lifespan. So that's how it's powered. So you don't have to worry about solar power. A lot of things, the previous rovers, Spirit and Opportunity, were running on solar power. And of course, dust storms, the solar panels just got covered in dust, and that was a real problem. Okay, now this is a nice little video here. Ingenuity, this is a model of which I brought along, a little Lego model that I've made off the rover. You can come and have a look at it if you wish. And there's a little helicopter. So this was very interesting. So they took a little helicopter to see how it fly. They used a twin rotor system because the atmosphere on Mars has less than 1% of the density of the atmosphere on Earth. So very, very thin. But they got it to fly 72 flights over 3 years. They used it as an aerial scout. So the rover's, sort of yay big and can go only so fast, but it could fly out and look for interesting areas to send the rover to explore. So here we go. It was originally stored in the belly underneath the rover when it landed. That's where it was. So it's obviously driving well clear of it. So once again, this is an animation, obviously. That's solar powered, that then charges an ion battery. That's how this is powered. See the advantage of it? Now it's able to see long distances. Yes. Oh, not a great sound. This is animation, yeah, to illustrate a point, yeah. So unfortunately that had an accident after 3 years, and it's, one of its blades got broken and it can no longer fly. But it flew for 3 years, 72 missions, pretty cool. Yeah, particularly the technology, less than 1% of the density of the atmosphere on Earth. But yeah, they got it to fly.
It was only designed for like a few flights.
Yeah. So it far exceeded their expectations. Yeah, fantastic. Okay, let's now go to destination Jezero crater, and on the end of it's up here on the northern eastern edge of a volcanic region. This whole area here is a big volcanic area, Syrtis Major, and it's sitting up right in there. That's where it is. And I've got a whole big stack of visuals for you so you can get a good feel of what the crater's like and what the rover's seeing. So first of all, let's zoom in on the crater itself. So this is 45 kilometres across. To give you an idea, that's about 1.5 times the size of Lake Taupo. The circle here is actually just a small volcano just to the side of it there. So that's the crater looking down on it all there, probably from an asteroid impact. They estimate it's probably 3.8 to 4 billion years old, the actual crater. And once again, you can see a nice hard lake bed of sediment, predominantly clay all here. But look over here, look at this, what you can see meandering around. It's a river. And here is, we were talking about early on, here is what we call a river delta, where all the sediment comes down through the river and then spreads out into a body of water. So this really got NASA's interest. This is an artist's impression of probably what the crater looked like when it was full of water and it was a lake. And you can see the river system here flowing into it, and you've got a river outlet system here as well. So implying the lake was, the crater was completely full with one big lake, about 3.8 billion years ago. And I just put it in context here, Gale crater, where Curiosity landed, about 3.6 billion years ago. That was found to be habitable. So they're now exploring another area that's another couple of 100 million years older. Yeah, there you go, there's Lake Taupo. So in comparison, so the lake here in Jezero crater is about 1.5 times the size of Lake Taupo. Just puts it in perspective. It's a decent sized body of water. Very decent. Amongst the crater, this was the area naturally of concern, well, of interest here. You can see the river system flowing down here, forming this delta. So this is the area that was explored by Perseverance. This was its landing zone here. But also of interest, they obviously had the photographic from the orbiters, so they knew where they were going to be landing and of interest. But what got them very interested in, they do spectroscopy from up in orbit around the planet, and they can get a fair idea of what sort of minerals and rocks, very rough sort of guide. And a lot of this region here was very rich in carbonate rocks. So carbonate rocks are rocks that have been altered by the presence of water and carbon dioxide in particular dissolved in the water. So you've got a carbon dioxide atmosphere, and water is a great sink for carbon dioxide. So you've got carbon dioxide in water that's reacted with the rocks, and that forms these carbonate types of rocks. Now you think, okay, well that's interesting, you're good-o. Here's the catch. Carbonate rocks is really conducive for supporting life. It's got little, there's just the crystalline structure of carbonate, and it's full of minerals in it there as well that are very rich for microbes to live on. But the other thing is, the real bonus is due to the crystalline structure of carbonates, they preserve fossils really, really nicely for billions of years, where microbes, that once they die, they remain fossilized within the carbonate. So as soon as they saw flowing water into a large body of water with this big delta of sediment here, rich in carbonate rocks, wow, that's where the money is. That's where you're going to put your rover. This is just a more close-up one here. You can see there's the landing site, but look at all the sediment that's just obviously been carried down by the river and just flowed out into the stable body of water, namely at the lake. Now here's some nice panoramic shots. So we're going to scan across here. So this is a 360-degree panorama by the Mars-Cam Z at the landing site. That's high definition, and it can zoom around. So you're looking here, here's the landing site, and you're looking across the crater to the far crater rim. That's what you're looking at here. The crater rim is about 1,200 meters high, so it's over 1 kilometer high, these rims here. You're looking across about 40 kilometers there. So let's have a look. Let's just zoom it up a little bit. So it just gives you a good idea of what it's like on Mars in one of these big craters. Look at those sharp rocks too. That's sort of pretty rough on the wheels. So that's just a nice little zoom of what it's like in there. this is another one. So that was looking away. That was looking that direction. This time it's turned around its camera and it's looking back up the river delta, back up to the mouth of the river. So that's the river flowing down here towards the delta. So you're looking back up that way.
Chris, why is the sky white?
It's a sort of a greyish colour because you don't have a thick density and why is our sky blue? Nitrogen, light bounces off and it's in the thicker atmosphere. So you've got a thin atmosphere of carbon dioxide, so it looks that pale sort of colour. So I hope that gives you, good visual effect of what it's actually like. Here's another one here. So this is looking across the delta. So first we were looking across the crater, then we were looking up the mouth of the river. We're now looking across the delta like that from here. And once again, look at all those, the rocks and all this, all these sediment, stratified sediment layers here. But all these rocks, clearly have been worn down by wind and water with sharp edges as well. Here's a nice little video it's a real movie taken by Perseverance in and around the.
After 1,000 sunrises on Mars, here's where NASA's Perseverance rover is exploring now. A river environment, billions of years old, that tells a dynamic story of the forces that shaped it. Let's take a tour of this area and see where we'll send the rover next. Perseverance is exploring Jezero Crater, where an ancient lake and river system once existed. If microbes ever lived here, signs of them could be preserved in these rocks. About 3.5 billion years ago, a river carved a canyon through the crater rim, filling the crater with water and depositing sand and rocks that formed a delta. On Earth, the record of such an ancient river and lake would have been erased long ago. That's why sending a robotic explorer like Perseverance is so valuable. Mars is a special place that preserves a unique record of things that happened in the first billion years of the solar system. In this area, different rock layers record different parts of the crater's history. The flat, light-colored rocks were deposited on the banks of a river flowing slowly across the landscape. The boulders in the distance were deposited later in what was likely a raging torrent. And if this peculiar outcrop caught your attention, it did ours as well. It doesn't look like sediment at all. Perhaps it's a remnant of a lava flow, now mostly eroded away. Lab equipment on Earth can accurately measure when a volcanic rock was formed, so if we can return a sample of this lava to Earth in the future, we may know when and for how long water flowed into Jezero. From here, Perseverance will continue west. In the distance, you can trace the tops of the natural levees that formed at the near and far banks of the river. The rover will pass this area on its way upstream, continuing toward this spot where the river carved through the crater wall. You can see the canyon on the horizon here. From there, Perseverance will be well positioned to head south and ascend this natural ramp that leads up and out of the crater. We're lucky to have a route the rover can safely drive up the rim right where we need it. Starting the climb would mark a new and exciting phase of the mission, exploring rocks far older than those in Jezero and produced in an entirely different way. One tempting target are these light-colored rocks partway up the rim. They may have interacted with hot water in a hydrothermal environment, another exciting place to hunt for evidence of past life. Since finishing its study of the crater floor, Perseverance has been climbing the delta and piecing together the history of this once watery environment. We've come a long way in nearly 3 years of exploring and collecting samples, but there's still so much more to investigate. Follow the journey at mars.nasa.gov/perseverance.
This beautiful mosaic is the most detailed image ever taken on the surface of Mars. It captures some of the sedimentary rocks that scientists came to the red planet to study. Only the very edges of the rover are visible in this mosaic. NASA's Perseverance Mars rover is now exploring a really important part of Jezero Crater. Around 3.5 billion years ago, a river flowed into Lake Jezero, depositing mud and sand on the crater floor, forming an ancient delta. What you see are some of the hills and cliffs at the edge of that delta. Here you can see some of Perseverance's wheel tracks, showing where we came from on the crater floor, where we spent the first year of our mission. Take a look at the darker gray layered rocks that make up the roughly 32-foot-tall cliff in front of the rover. You can see very clear horizontal layers in these rocks. And you'll also notice pieces of the cliff have broken off and tumbled downhill. One of the more interesting ones is the 3-foot-tall boulder called Betty's Rock, which Perseverance was able to get a closer look at. These rocks have been sitting on the surface of Mars for billions of years. And over that time, wind erosion has shaped the surface into pretty interesting forms, like this balanced rock. Immediately surrounding the rover is an area called Hogwallow Flats, previously known as the Bacon Strip, based on its appearance in orbital images. Take a look at the bright rocks the rover is sitting on. We think these are some of the finest grained sedimentary rocks deposited in the delta. Fine-grained rocks are important because they're typically really good places to look for signs of ancient life. We'd plan to do up to 5 abrasions on the rocks in this area. That's where we use our drill to expose a fresh surface, which allows us to analyze the chemistry and mineralogy. But Mars threw us some curveballs, and these softer rocks didn't always cooperate. Here you can see the results of one of our abrasion attempts. The rock crumbled during the abrasion, preventing us from analyzing the spot. We had 2 unlucky abrasion attempts in this area before achieving success at the Skinner Ridge outcrop. Here, we collected our first 2 rock core samples from the delta, and since then, we've collected 2 more. Perseverance drove to the delta because it is a very promising place to look for signs of ancient life. We hope to learn more when a future mission brings these samples back to Earth. So far, we're excited by what we've collected.
Yeah, and what it was like inside the crater. So that was a good look around Jezero Crater. Let's have a look at some of the discoveries that Perseverance has made in Jezero Crater and the implications. So let's have a look at some of these. Okay, so these are the 5 main ones here, which we'll look into. First of all, the evidence of an ancient lake and river system. And this here is a large mold of sediment called Pine Stand Hill. This stands about 20 metres high, but check out this, there was lots of large isolated mounds up to 250 metres high. That's a quarter of a kilometre up, huge mounds, just multiple layers of sedimentary rock. And to have deposited that huge amount of material like that in layers like that can really only be done by some sort of deep, powerful river. It's certainly not a shallow stream or anything like that. It had to have been a deep and a pretty powerful river to carry that much material around and build up layers like that.
So, Chris, if I may, ebbs and flows.
Yes.
Yeah, because otherwise it would disappear almost all at once.
Yep, correct, yeah. So it was a very dynamic place. It wasn't just little shallow streams going on. It was real deep, powerful river flows, absolutely. So the implications of that is that the layers of mudstone and carbonate-rich deposits provide evidence for a deep river and lake, as these as well. And as we mentioned before, mud and carbonates form in aqueous environments. They support life and importantly preserve fossils, life form fossils as well. So discovering areas like this, these big mounds, certainly had a lot of significance in there. Then they found these bands of rocks. So you can see these rocks sort of all laid out in bands. And certainly on Earth, you find those likely formed by once again, by a fast, deep, powerful river, and possibly sandbars as well would have done that. So that's a little area called Shrinkle Haven. So these are some of the different sort of what we call morphology, some of the different patterns and structures that it's seen there within the crater. And each of those give clues to the conditions of what it would have been like. Here's another one. Now, where you see all these deposits sort of spreading out like this. That's classical. Where do you see that on Earth? That's shoreline, classic shoreline structures. And this area here is called margin unit, and that's sort of, they've labelled it like a beachfront, if you will. Here's a comparable shoreline on Earth. You see all the layers and stuff, the way it's laid out. So when they saw this, they thought, that looks like a shoreline, almost certainly. And when you see the shoreline, that implies to get a shoreline like that, you need large, long-lasting, it takes millions of years to form shoreline structures like that. So obviously there was that lake that was there existed for millions of years. That's what that pattern tells you, the implications of that. We know that the delta formation from there, and it goes into the handout how they tell surfaces and that through crater counting, but the delta formation was about 3.7 billion years old, so about 100 million years after the crater was first formed. And they certainly know that habitability began earlier and lasted longer than inferred from the delta formation for this to have all occurred. So immediately, remember, curiosity said, well, we know that Mars was habitable out to 3.6 billion years. This is evidence that Mars was quite habitable, quite capable of supporting life out to 3.7 billion years. So the conclusion from that little bit of looking around at those structures there was that the whole system is 3.8 to 4 billion years old. And it's the implication, because the delta is about 3.7, but it looks like that was supporting life. So the general consensus is that crater, the whole lake system, could have supported life as early as 3.8 billion years ago. So that's automatically significant shift. 200 million years, that's a long time to suddenly extend that Mars was quite capable of supporting life.
So, Chris, where did all this water come from?
Yep, it had a water cycle. Originally, it would have come from like Earth got its water, twofold, intrinsically, just within chemicals within the ground that comes up, and extrinsically from comets and asteroids. So exactly where we got it from. How did it then find its way into rivers and then into lake? There's a lot of evidence that they had precipitation, snow and rainfall on Mars, a water cycle, yep. And it would have come down from the highlands, probably a lot under the surface as well. That those Casia canyons that I showed earlier on, that water would have just suddenly would just burst up out and created gushes of water. So volcanic rocks as well. And this is an area of, you can see this here, that's basalt rocks, not sedimentary rock. So basalt rock is a type of what we call igneous rock, rocks that's formed from magma and lava that's then cooled down. This is an area called Mars Formation. Now the relevance of this, you might say, well, they found some volcanic rock. Yeah, sure, we know there was volcanoes on Mars, absolutely. These rocks have been altered by water when they examined them. So clearly there was an overlap between Mars being hot and volcanic and also wet and just cooling down and being habitable. Basalt rocks, the other relevant thing is basalt rocks are much larger than sedimentary rock. The other thing is that if you can get these back, sedimentary rock is only so far you can sort of get an idea of dating. It's not really reliable. Basaltic rock, any sort of igneous volcanic rock, yeah, you can radioactive date it very, very accurately. So we know that these rocks were altered by water. If you can get these samples back to Earth, that will give you a much better idea of the whole time frame. So yeah, so it tells that Mars history involved both hot volcanic and wet sedimentary processes that probably overlapped, and it's just going to give us a better complete geological picture and evolution. It also says that a much more ancient environment was also suitable for microbial life. So we know these are some of the oldest rocks on Mars. They were certainly in contact with water to form the carbonates, minerals that were formed from those rocks. So that immediately tells you that Mars was habitable, probably even before 3.8 billion years ago. And it also suggests that it was not only early, but prolonged and widespread water for them to have seen this. So this is possibly, these rocks here are possibly the key to unlocking Mars's geological and climate history. to reveal exactly when it was wet and potentially habitable. The answer will be in these rocks, which they have samples. They're ready to come back to Earth, but there's not the political will to bring them back. So very sad. Don't get me started on that, please. But there were plans to bring them back, but they've been shelved. Meanwhile, they're building ballrooms. Sorry. Potential biosignatures. So these what they call leopard spots, and these are you can see them here, and they're little circular patterns of iron minerals that form these little patterns in here. Let's have a close up. That's it there. To there. Looks a bit grainy there, but they are called leopard spots. And essentially, the ring-shaped patterns in the rocks, they are formed from distinct iron-rich minerals that are seen on Earth as metabolites of microbial metabolism, where microbials have been getting energy from the rock and they produce these iron minerals. So there's vivianite, which is iron phosphate. That on Earth is seen from the decay of organic matter. There was gregite identified in there, which is iron sulfide, which is a microbial metabolic byproduct. So you know how we take in oxygen and we eat plants and so on for our food, or we eat organic stuff. A lot of microbials, they get their nutrition from rocks. When you have your sandwich at lunchtime, essentially what you're eating is electrons. It's what we call the electron chain. We're taking electrons on board to drive what we call electron transport chain, which then drives a chemical gradient, form a thing called ATP, which is energy, which keeps us moving along. And so a lot of microbes get their electrons from what we call reduction and oxidation, or redox chemical reactions from the rocks, and that's how they get their electrons. So this looks to be in Earth. Gregite or iron sulfide is a microbial metabolic byproduct. It can, however, be formed from abiotic chemical reactions, in other words, reactions that don't form from life. Once again, it needs to come back to Earth where they'll give it a definitive answer. But this is the strongest evidence to date of some sort of signs that actually was not just habitable, but habited, that Mars actually did have microbial life on it. This is the best evidence to date. So then there was sample collection and technology demonstrations. We've talked about this, how they're able to take nice core samples in good condition, preserve them, put them in Titanic tubes, and ready to be taken back home for chemical analysis and high-end laboratories on Earth, but also accurate dating, particularly those basalt rocks. Then there was MOXIE, you saw on the instrument. So that operated for 3 years, and in that time, it was very successful. From carbon dioxide in the atmosphere, they created 122 grams of oxygen, 98% pure. So it'd be perfectly fine for breathing, and of course you can use it for rocket fuel as well. And then we spoke about Ingenuity, the helicopter there, powered flight, showed that it was possible in the very thin atmosphere. So all of these three things here has implications for further missions going back to Mars. We know we can utilize the atmosphere. We know that you can get some sort of flight, drone helicopter flight, powered flight working, and there's samples to be collected and bring back home again. Then there was that REMFAX, the subsurface imaging. So that showed a lot of interesting stuff as well. And that showed that the crater, the subsurface, the underneath the lake bed, if you will, was not uniform, just nice little sediment layers spread out like that. It was quite complex. And those horizontal layers, instead of being laid out, some of them are actually tilted up to 15 degrees. That's quite some angle. And the implications of that, for those certain layers of sedimentary rock to have tilted, that takes time. Obviously, some ends of it were heavier minerals, and that some parts of it sunk down in relation to other parts, and it tilted and it created the structure. That would take some time. So it tells us that the delta area and the laying down of the delta happened over a very long time, probably millions of years.
Sorry, Chris.
Yeah.
Doesn't that suggest that the surface is moving?
That would be, once again, with water as well. They mainly said, look, it's a lot of the heavy minerals that would be sinking and moving as well, was the main thing there. But
movement like we have on Earth.
No, Mars is a one-plate planet. There's no tectonic plates on Mars. Yep. The other thing is that it did show is that it's the younger upper horizontal layers are the most sustained, most stable, and your best chance of finding your biosignatures. They're able to work that out as well. 10 meters deep, it's able to examine the geology of Earth just by, with radar, sending down radio signals and seeing them how they reflect back again. Amazing technology. So let's sum up. I've got another nice little NASA video.
Mars is the closest place that we can reach with robotic exploration that we think had a really good chance of having ancient life.
The Perseverance rover will land at a location called Jezero Crater. Jezero Crater is a very interesting place. It's a crater that once held a lake.
There are a lot of craters on the surface of Mars that could have once hosted ancient lakes, but not every crater that we think had a lake actually preserves evidence that that lake was there.
It had an inflow channel and it had an outflow channel. That means it was filled, the crater was filled with water.
In Jezero, we have probably one of the most beautifully preserved delta deposits on Mars in that crater.
This is a wonderful place to live for microorganisms, and it is also a wonderful place for those microorganisms to be preserved so that we can find them now so many billions of years later.
There is no other place on Mars that has the unique combination of a lake setting, a beautifully preserved delta, and the diverse mineralogy that we have in Jezero Crater. So it's truly a special landing site.
The major goal of the Perseverance mission is to investigate astrobiology on Mars, and in particular, to address the question of whether life ever existed on Mars. The Perseverance rover starts with a design that's very similar to Curiosity, but we've added to it a whole new set of science instruments. And these science instruments were purposefully selected to help us in the search for biosignatures.
We're going to be taking microphones with us. For the first time, we're going to have that human sense on another planet.
Perseverance carries with her a grand experiment in spacefaring technology, a helicopter, the name of which is now Ingenuity.
One of the major upgrades that Perseverance has from Curiosity is that it's able to self-drive for a distance of up to 200 meters per day. As the rover is driving, it's literally building the map of the road it's driving on Mars.
Scientists for years have told us that to really unlock the secrets of Mars, we have to bring samples from Mars back to Earth.
So what Mars 2020 is going to do is to drill samples, put them in small tubes. We're going to seal it in its own individual tube. We set them on the surface to provide a target for the second two missions, which hopefully will get in development in the next several years and could potentially get the samples back to Earth by 2031.
Perseverance is a very, very profound first step in both our understanding of our place in the universe and a stepping stone towards human exploration on Mars.
And those treads you saw are made of titanium, so they've redesigned the wheels. So that's a bit of a summary. Conclusion that Perseverance has showed up and above what we already learned about in our first chapter, what we knew before Perseverance. So it confirmed liquid water and energy sources in both surface and subsurface environments. So microbes above the surface and below the surface would have been quite happy to have survived there. Mars was habitable over 3.8 billion years. Prior to that, we're just aware of 3.6 billion years, and probably extending for at least 2 to 3 billion years of habitability of Mars could have supported life. In fact, there's a lot of evidence to suggest that around some of that time, 3.6 billion years ago, the conditions on Mars were more favourable for microbes and life than they were on Earth at that stage in time too. And of course, they now found a potential biosignature has been discovered. So we'll know more when it comes back to Earth. And that's the NASA's Perseverance rover searching for ancient life on Mars. Thank you. Yeah. Any questions?